Alright, so this is where we left off the last time. I apologize, I was upping the resolution on the machine. So let's have a look here. Can we predict differentiation? So one of the questions that I was asking myself is, what if there are two types of cells on day 7 and we can identify them by fitting a day 2 model. So on day 2 we have a model and then we fit it to all the cells on day 7, and I was in my mind hoping for a perfect bimodal peak where it fits half the cells well that haven't differentiated and half the other cells it doesn't fit. Turns out nature is not conducive, so it gave me a single peak anyway, but you do see some broadening. So if we compare using day 2 to predict day 3 on the right versus day 7 on the left, there is some bimodalness maybe. However, if you split at 0.56 and then you know do a different fit for each of those two groups, it doesn't actually improve anything. But we do clearly see two different groups. So if you do k-means, which does not care about the y data, it's only using the x data for the gene availability, and it's going to tell us, okay, I want 5 clusters, here are my 5 clusters. Well, turns out there are 2. And so this is something that nobody has told us. You know, they tell us there are like 7 different cell types, but nobody tells us that there are these 2 types of cells, and I would be interested to know what's going on there. But then if you look at them more carefully, you see that indeed one type of cell, the predominant one on day 7, is the one that is responsible for the decay. So 67.5 is perfectly fine. 67 is up here, close to day 3 and day 4. So uh, one of these groups is performing perfectly and the other one is not. And so that's already a very interesting finding. Nobody knows what these mystery groups are, I don't think. But let's have a look at what PCAs are affected. So the top 64 PCAs are both unaffected. In fact, the group that performs worse, predicting its PCA, you do a slightly better job. And the same with 512, 1000, 2048. Only when you go up to 4000 PCAs do we see this huge drop suddenly. Right? So somewhere between PCA 2000 and 4000, day 7 cells have a lot of noise, but only one group, only one of these two groups has a lot of noise. And so you might imagine it doesn't have much of an impact on protein production. But at the same time, the other effect is that the PCA is different, right? So here I'm predicting from same day, the PCA 64. If I predicted from a different day, say from day 2, predicting day 7, the PCA performance would be worse. So there's two different effects for day 7. And you can see here, if you break it up into these, the MASP and EUP and HSC cells are the ones that are mostly in this second group, although not exclusively. All right. And so here, okay, how do you win this competition? Well, I didn't win it. I didn't even get close. But there are these kind of two effects happening on day 7, which is the late day is what you are looking to predict in the private test. One of them is to predict the new PCA components, and the other one is to predict this noise with PCA over 2048. Turns out you can't do either of them. All right, so the spotlight conclusion here is that the day 7 cells have changed, maybe due to differentiation. We are dealing with stem cells after all, maybe not. Changed here means the PCA components can be predicted from same day but not from other day cells, and that somehow random protein buildup has spoiled, has introduced some other noise. So those are the two effects that we have observed, and these are the conclusions that we are drawing from them. All right, so um, let's go and compute some correlated features. So this is one of the things that you should always do when model building. When you have a good model, don't stop. For example, if you have a model that uses the PCAs, why don't you go find a model that doesn't use PCAs? Right. So here, this is something that Ahmed El Fazouan did, and um, he wasn't happy to just do one model. He wanted to do 140 models, one for each protein. And for each protein, he picked 800 genes that were the most correlated with that protein. And turns out he got a good performance, right? So he got a very good performance on just protein 0. His 800 proteins did better than using the PCAs. And so once you go and you do that for all the proteins now, you find that, again, actually this time you have about the same performance, now slightly worse. Turns out protein 0 was not completely representative. And worst of all, you can, if you do single proteins, you cannot no longer use the correlation as your target, because you can only use mean square error. And at the end of the day, you know, that's not as much of a problem, but somehow using PCA has the correlations built in, right? So even if you optimize on mean square error using the PCAs, you get this correlation built in. So it turns out you get 6% extra correlation just for free, just because you're so clever as to use the PCAs rather than the single genes. However, there is a quick fix, which is you just slap all the 800 genes for each protein, for all the proteins together. It turns out a lot of them overlap. You get about 8,000. And then you use those 8,000 rather than the 20-odd thousand that you had as raw features. And that turns out to be adequate. And so you can essentially put them together, and so you have an ensemble, right? An ensemble model. Turns out the best split you get is 4:1, um, and uh, and you get a small improvement, I believe, 0.2% in the correlation for doing it that way. But now you also have a model that just uses the genes as input, not the PCAs. So if you're a synthetic biologist, you like using the genes, you don't like the PCA, well, you're in luck, there's a way to do it. All right, so now I had the idea of doing the same thing for multi-ohm. He says it doesn't work. However, I talked to somebody at JBay, um, and he told me, you could maybe just look at the PCA and the top genes of each PCA, and then sum all the absolute values of all the weights in the PCAs, um, and weigh them by the explained variance. That's something I came up with. But anyway, so again, you can do this, and you can use genes by themselves, and you can. This time it's not quite as successful. You need a 9:1 split, but it still works, and you still have a model that uses the genes themselves, not the PCAs, as an underlying thing, and it does almost as well. Um, yeah, so as you can see, it's only 0.5% worse than using the PCA, but you do need to use 26,000 genes, so it's not nothing versus just using 40 input features. All right, so then I was asking myself, well, what if you change the number of genes that you include? So I already mentioned you can do pretty well here if you include 26,000. How about if you just include 10 or 1? And so here is the plot that, how well can you do with just 1 gene or 10 genes. Of course, you would choose the best one, the one that has the highest overall importance in the PCAs. And it turns out you get this log plot. If you use no genes, just always predict the average, you get 64. And if you use the PCA, you get 68. So the 4% is your playroom. That's all you get. And within that playroom, just using a single gene, you get 3/4 of the way. And so that's already pretty impressive, right? But there are hundreds of those genes, and maybe even thousands, and so on and so forth. So turns out that to predict kind of like the principal knob that the cell turns for its metabolism, there are many genes that correlate mostly with that principal knob. And so predicting those genes is similar to predicting that principal knob, which gets you 3/4 of the way there. So it all goes back to the PCA in the end. But if you look at these genes, well, what are these genes, these most important genes for the metabolism? Well, they are more non-zero than other genes, as you might imagine. They're more active. On average, maybe 8 or 9%, so 4 times as active or 5 times as active. But you can also go the other way around. You can say, well, the fourth one here on chromosome 3 is only active 3.6% of the time, and it gives me 3/4 of the correlation boost from 64 to 68, 3/4 of the way there. So I can already explain 3/4 of the improved correlation with just 3.6% of the cells, and just say the other cells aren't doing anything. If you're looking to find cells that are important or that are the most active, that you want to pay most attention to, you may be able to just not just disregard 96% of the cells. For conclusions, we have this upside down, turning the pyramid upside down, where we go from little to big rather than going from big to small, as you would do with the gene basis. We found a way to use genes, though, rather than using PCAs with a small penalty. And then I was asking myself, well, how well do we do with predicting the raw protein levels, right? How much better are we than just always predicting the mean? And I already mentioned that predicting the mean is, in most cases, already a really good strategy. So for the multi-ohm data, we only got a 4% improvement from using all the genes. And for the site-sec data, we went from 72 to 89. That's a bigger jump. That's a 17% jump, right? So we do more, and so this is the site-sec data. And so if we predict one, our prediction is usually one standard deviation away from the true ground truth of protein expression, then that's basically the same as random guessing, or the same as always predicting the mean, right? Because that's the definition of a standard deviation. And so here we have this huge high bar, this huge maximum at 1, just like you would expect. And then on the left and the right, we have, expect this kind of bell curve. But we have a model, we don't just have random guessing. And so we actually do better than that. And in fact, we have this long tail. Some proteins we can pin down to half a standard deviation accuracy. So we have about 30 proteins here that we actually kind of like cracked a little bit. So we can get them within like 0.7 standard deviations rather than 1 standard deviation. So that's the achievement of this model. But at the same time, predicting correlation is easier than predicting raw levels. You can already see, right? We can predict correlation with 89% accuracy, and that's one of the reasons is that the mean, using the mean is already getting us 72% of the way there. And so yeah, here you see the same plot using the raw gene data as inset rather than using the PCAs, and you see we do slightly worse. Okay, success story of using PCA in correlation to predict protein levels with this much correlation. Most of that is just by predicting the mean, right? Turns out 97%, I believe, or 96% you can get by just predicting the mean times 72. So it's really, the improvement should be from 96 times 72, so I don't know what that is, it's probably around 70, to 86. So we get an 13% improvement by actually doing a model and using X data. So what we learned is here we can use individual level for the multi-ohm. There are a lot less knobs, just 40 knobs turns out for the cell, for these kind of healthy cells. And then that all but 2% of correlations can be deduced from gene availability. Only one single gene, right? So it's an extreme way of putting it, but yeah, you do well with just using a single gene. And then we saw these two features on day 7. I already discussed those. We can use more data. It would be nice to have protein and DNA data. Nice to have time series data for the same cell, site-sec data for day 7. We'd like to know what those clusters are. K-means found 2 clusters. What are those, right? And here are all my failed attempts if you really want to look at those. I wrote probably more like over 40 notebooks, but definitely lots of notebooks, lots of work time, and I just wanted to, at the end I put this statistic together based on a post by the Kaggle team, and so if you just assume 3 hours per submission, which I spent over 20 hours per submission, but if you just assume 3 hours, then over 32 person years were spent on this competition. So that's a huge investment. And a lot of it, of course, was doing the same thing. 1,000 people doing the same thing. So you're training 1,000 people to do very basic work, whereas if you had one actual person doing 32 years of work, they would probably be able to do a lot more, but who knows, they might run into lots of blind alleys because they make mistakes. Yeah, thank you everybody for helping me. I was very excited when I saw all these posts by the grandmasters, and my own model I got from 64 to 66, and I was so excited. And then I saw the post, and I was like, well, okay, this just does 68, and I don't have to do anything. So anyway, very humbling.